Good afternoon, everyone. I hope you are all doing well, and I'm very happy that you have been able to join us today in this MS&T 2020 meeting on additive manufacturing. In the next half an hour, we are going to be discussing grain growth and particularly calculations of grain growth. The contents we plan to discuss the way the grain structure changes with time because of heating and cooling, how with different locations the grain shape and size changes within the part, and then how the columnar to equiax transition actually take place and how we can predict when that would occur. And finally, how the scanning strategy can change the texture. And why do we want to do these topics? Well, this is because the grain structure is very important for the mechanical properties of the material and therefore the serviceability of the parts that we produce by additive manufacturing. We show here, for example, that the smaller grains are stronger for additively manufactured materials, and we are plotting the inverse of the square root of grain size, and we are seeing how the stress changes. So how do we actually calculate the grain structure evolution? Well, we want to first of all calculate very accurately the temperature field and how that temperature field in the entire component changes with time. That is very important because that drives the change in grain structure as a function of time. So how do we calculate the change in temperature at all locations of the part as a function of time? Well, we use a well-tested three-dimensional transient heat transfer and fluid flow model. And once we have received the reliable values and tested the values, we use that to calculate grain growth. And the specific technique that we use to calculate grain growth is the Monte Carlo technique. So we are going to be talking a little bit about how we use Monte Carlo and then how we calculate grain growth. So first is heat transfer and fluid flow model. In order to get the accurate three-dimensional transient temperature field, we discretize the entire build, the part that has been built and the part that has not yet been built. So we subdivide the component or the part into many small parts, many small cubes or rectangles. And let's say that we are building a wall, very simple situation, and we want to divide that into about 250,000 cells. And there are three components of liquid metal velocities, pressure, and enthalpy. These five variables we want to solve. So we now have five variables and 250,000 cells. So we have 1.25 million algebraic equations that represent balance of various quantities within each cell. We do this iteratively because we initially do not know the values of these variables. So we get about 100 iterations per time step, 1/8 of a billion equations per time step. And if we are doing a simple calculation in which we take only 1,000 steps, 1,000 time steps, we are looking at about 125 billion total equations. And these equations, when we can solve them, will give us the transient temperature and velocity fields, cooling rates, the solidification growth rates, the temperature gradients, the whole set of parameters that we want to know. And the input to this model obviously will be the process parameters, the speed, power density, and the material properties, the properties of the alloy that is being used to build this particular wall. So it's a very huge task, and once we solve it, we can calculate the temperature fields. For example, we find that the liquid from the middle is moving to the periphery. And I'm showing you a cutaway view, only one half of the fusion zone or melt zone, in which the liquid metal is moving from the middle to the periphery, turning around and going to recirculate throughout. And if you look at the velocities of this flow, typically they are less than a meter a second, but still you can see that this is circulating quite vigorously, and so the liquid can be viewed as more or less very well mixed. And this velocity also mixes the hot fluids with the cold fluids. Right in the middle, right underneath the laser beam, the temperature is maximum in this liquid pool. So this hot liquid is moving towards the edge, mixing with the cold fluid, going down, and they are circulating in the way that you see here. This particular flow is primarily driven by Marangoni convection. Marangoni convection here occurs because of the spatial gradient of interfacial tension. The spatial gradient of interfacial tension is a stress, and that stress is what is causing this flow of liquid metal. And this temperature field is very important for us because correct temperature is obtained when we consider all mechanisms of heat transfer. That means heat is transported within the liquid pool by conduction as well as by convection due to the flow of liquid metal, and then heat is also radiated from the surface of the pool to the surroundings. And if I take a particular monitoring location here shown by this red dot, you can see how the temperature is changing as a function of time. And this is a titanium 6 aluminum 4 vanadium part that is being built. And you can clearly see that as more layers are built, you are getting temperature versus time plots that involve both repeated heating and cooling. And it is this repeated heating and cooling that is responsible for the change in the grain structure. That's our starting point. You have seen some calculation schemes where people have not considered the flow of liquid metal. They have taken the heat conduction equation, which makes life a little simpler because we are not solving Navier-Stokes equation, we are not solving the velocity fields, and therefore the calculation scheme would be easier. However, there is a penalty to be paid. If we don't allow the hot fluid to mix with the cold fluid, right in the middle, right underneath the laser beam, the temperatures would be unrealistically high. We are plotting here the cooling rate as a function of laser power. And you can see that if we take the conduction and convection, then the temperature of the liquid pool, the peak temperature, will be lower. That's because you are mixing the hot and the cold fluid. If you don't allow that heat to be transported to other regions, as you saw in the movie that I showed you about how the fluid flows, then the hot and the cold fluid, they do not mix, and therefore the peak temperature is unrealistically high, and therefore we get a higher cooling rate if we don't consider convection. In other words, heat conduction models always overestimate the peak temperature as well as the cooling rate. So we do have to consider fluid flow effects if we are going to be looking at the grain growth. The grain growth model starts with 3D transient heat transfer and fluid flow model that gives us the temperature field, the thermal cycles, and the solidification parameters, specifically the temperature gradients at all points, and also the solidification growth rate at the solid-liquid interface. If we take the three-dimensional Monte Carlo grain growth model and supply all those information, then we'll be getting as output of the Monte Carlo model the time-dependent spatial distribution of grain structure and grain morphology, size, and all parameters of the grain that are very difficult to determine experimentally, because in a virtual experiment, you can section as many sections as you want along whatever direction you want, and therefore you will get a more complete picture of the grain structure evolution. So the Monte Carlo grain growth model. What we do is the entire part where there is heating and cooling, we discretize. We have different grid points, and in each grid point we assign an orientation number between 1 and 32. Why 1 and 32 when the grains can be oriented in three-dimensional space in any number of ways? Infinite number of orientations are possible. We take 1 to 32 because we have found by doing many simulations that if we take more than 32, we still get the same result. Here you can view 32 as if 32 is our infinity. Doing more calculations do not give us any more accurate results. Step 2, after we have assigned the orientations, we want to calculate the interaction energy between any particular grid point and its nearest neighbors. So if I have n number of nearest neighbors, we can figure out how many of those neighbors have different orientation. If they have a different orientation, we assign some energy. But if they have the same orientation, then the energy is zero. Energy of interaction is zero. That is our starting point. And then after we have done that, we select a random grid point and we select then its neighbors, and we change orientation to one of the nearest neighbor orientation. So at least two of the points will have the same orientation, and we recalculate the total energy after that change. Once we have recalculated this change, we then calculate the total energy. If the energy is negative, then we allow that change to take place. If the energy is not negative, then we assign a probability of change of orientation that is less than 1. And this process is repeated throughout until we see a change in grain structure. Once we have done that, we will get a simulation like this, where the blue area is the liquid pool. As it moves, you can see long columnar grains are formed, they bend, and that is how we are seeing how the grains are forming and they are growing because of the heating and cooling. So at the end of our simulation, we have to figure out how good is our simulation. We are trying to do just that here. We do the simulation and then we go ahead and do an experiment, and we see in different sections how the grain structure in different layers are actually matching with the experiment. That is how we determine the fidelity of the model. And we calculate also the average grain size, the grain size distribution, the topological distribution predicted by the grain growth model. Also important would be how the grain structures can be calculated as a function of process variables. So I am showing here what happens if we change the scanning speed from about 15 millimeter per second to 25 millimeter per second. Maybe the orientation of the grains should be somewhat different. Maybe the size of the grains would be somewhat different. If the temperatures are higher, then we can expect the grains to grow little more because it will have little more time. So this type of calculations, and I'm showing you the top view of the deposit to build an Inconel 718 part. And after doing experiment, we can compare the calculated results with the simulated results. This is showing as a function of time what happens to the structure, how the grain structure evolves in an aluminum 6082 alloy. The important thing here is that we are able to actually see what happens and how the grain structure evolves. So this is not a post-mortem only. It gives you an insight that is very difficult to obtain by simply doing experiments, because in an experiment it's difficult to find what happens as a function of time, and we can section it any location of the heat source and the grain structure variation at different planes we can see. And we can also see the morphology and the size of the grains. Very often during additive manufacturing, the grain structure is columnar, and columnar grains are vulnerable to formation of cracks. A little bit of strain or stress can split the grains apart. Solidification morphology, particularly if it is columnar, we would like to change it to equiaxed grain. And the tools we have are to control the solidification growth rate as well as the temperature gradient. I am showing here a vector that is perpendicular to the solid-liquid interface, and this is our growth direction. And so if we take a morphology index, that is temperature gradient G, divided by solidification growth rate, and solidification growth rate varies at different locations. We'll talk more about this later on, but this particular parameter G by R can change with location, and the consequence of that is that we may have columnar grains in certain areas in a big pool and equiaxed grains right in the middle here. So here we are showing how the columnar grains actually evolve, and the plot shows the G by R, the morphology parameter, as a function of distance from the edge of the well. This is the edge of the well. So as we go away from this edge in distance, the G by R changes, and this is for 2 millimeter per second. If we increase the speed, now the G by R changes to a smaller value, and if we increase the speed even further, now we are having G by R crossing this line that shows the distinction between equiaxed and columnar grains. So after the as we move from here downward, at this point, we start forming equiaxed grains. Different speeds, the curvature of the G by R as a function of distance is different, and therefore we are going to have lot more equiaxed grains here where we are using a higher velocity, higher scanning speed, and therefore we may expect more equiaxed grains at the faster speed here. If we look at the uh, scanning strategy, that means we may decide for the laser to scan only from right to left, as in this case. We will call this unidirectional scanning. And then we may also decide a zigzag scanning pattern. That means in one layer, we go from left to right. On the next layer, we change the direction of the laser beam. And we are making a multi-layer. Each layer, there is single pass and directed energy deposition of Inconel 718. The first step to understand the role of scanning pattern is to start with unidirectional scanning. In each layer, the laser beam goes from the left side to the right side. You get a pool where the temperature field is compressed along the scanning direction and elongated behind it. The maximum heat flow direction is shown by the yellow arrows here. So everywhere you look, whether it is at the beginning of the track or towards the end, the maximum flow of heat direction is at an angle with the scanning direction. So now we are going to be looking at how the dendrites are oriented if they are oriented along the heat flow direction, and we will be comparing that with the actual microstructure. This is our heat flow direction, and the middle one right here is showing the orientation of the primary dendrites about 60-degree angle to the scanning direction. And when we look at the actual micrograph, the orientation of the grains are also at a 60-degree angle with the scanning direction. There are many, many layers here. So this is the first layer, the second layer, third layer. So they are all aligned at 60 degree with the scanning direction. So you get a beautiful columnar grains that nobody wants. Long columnar grains are bad news for mechanical properties. They are susceptible to cracking. So what can we do? This is bidirectional laser scanning. We go from left to right in the first scan, then in the second scan, our direction changes from right to left. If you look at the first layer, the temperature fields are compressed ahead of the beam and they are expanded behind it. But if you look at the second layer, then this is how it looks like. It's compressed from right to left, but expanded thermal profiles from in the other direction. And so the primary direction of heat flow in the two layers are very different. Let me see if I can show it to you. In the first layer, this is the direction of heat flow. If you move to the second layer, the direction of the primary direction of heat flow changes. So it's because of the way the fusion zone would be oriented going from left to right or from right to left as it would be in the second layer. So um, this is our unidirectional heat flow direction, and the growth of the primary dendrites oriented along the same direction as the primary heat flow direction, and you get a continuous columnar growth. In the bidirectional scanning, the primary direction of heat flow changes, and therefore what happens is, if you look at the actual microstructure, In one case, the dendrites are growing at 60-degree or 45-degree angle to the horizontal direction, which is the direction of scanning. But if you go then to the next layer, the primary direction of heat flow changes, and so the orientation of the grain growth also changes. Most important, look here for the unidirectional flow. You have uninterrupted growth of these crystals at an angle 60 degrees with the scanning pattern. But then if you go to the bidirectional scanning, then at one layer it goes in one direction, the other layer the direction changes. The direction should have been at 60-degree angle. It doesn't become 60-degree angle exactly here experimentally. So there is some discrepancy here, about 15-degree deviation from the direction of the main heat flow, and we need to look at that. Bidirectional laser scanning, this is our primary direction of heat flow. So this angle is now not 90 degrees, but somewhat different. This is 60 degrees, and then it's going at 60 degrees to the direction of scanning, another 60 degrees. So this angle now becomes 120, but experimentally we find that this angle is actually 90 degree in the microstructure. So it's quite possible that, you see, this is the primary dendrite growth. The secondary dendrites are now at 90 degrees to the primary dendrites. And it's quite possible that the secondary dendrites are providing a nucleation site for the growth of the second layer, and then the third layer, and then the fourth layer, and then the fifth layer. So it's going at about 90 degrees rather than 120 degrees here between the two layers. But it's possible that because it cannot accommodate both the easy growth direction as well as the maximum heat flow direction, there is a competition between these two, and the eventual settlement is at 90 degrees, which is what we see in the microstructure. So in summary, a bidirectional scanning pattern would interrupt the unidirectional uninterrupted growth of columnar crystals, and therefore the microstructure and the properties would be much better than you would get in unidirectional scanning. The spatial distribution of grain size, we are actually plotting here the distance from the top surface where the heat source is. And as you go further away from the heat source, the crystals do not have that much of heating, so the growth of the crystals are not as pronounced. Very close to the heat source, the crystals are larger. As you go away from the heat source, either from the top surface or from the central plane, the crystal growth becomes less pronounced and we get smaller grain size. The distribution of the number of sides of the grains, we sometimes call that topological class distribution. In short, these are three-sided crystals. In the cross section, it will appear as if this is a triangle. And then you have this one, which is a pentagon in this section. This one is hexagon. So most of the crystals would be six-sided crystals, and there is a distribution which is typical of the grain size distribution. And this is true for whether we take it at the very top surface or we take the longitudinal central plane. But in each case, the frequency versus number of edges, or the topological class distribution, is independent of where we take the data, whether we take the data at the top surface or whether we take the data at the longitudinal central plane. So in short, if we want to do grain growth calculation, a prerequisite for that is heat and fluid flow calculation. Accurate values of transient temperature field is a critical requirement for this task. And then once we have that, we can use that temperature field for Monte Carlo calculation of grain growth, and the grain growth seems to be fairly accurate in this calculation. It satisfies the topological class distribution, and it can explain the role of scanning pattern on the solidification structure of multi-layer deposition. In other words, we can predict the texture fairly well. And the difference in texture that we get because of the variation of scanning pattern can be well predicted by numerical modeling using Monte Carlo simulation. Columnar to equiax transition also can be predicted by grain growth modeling, and control of process parameters in many cases can be used to control the grain structure. Thank you very much for your participation, and I would be happy to answer any questions you may have. Many of our recent writings are here, starting from our upcoming book on innovations in everyday engineering materials, and our reviews on scientific, technological, and economic issues in metal printing, and the role of metallurgy, mechanistic models, and machine learning in metal printing. All our other um, other works are available in our website, so please visit us here, and I would be glad to answer your questions. Thank you.